Hi everybody, and welcome to this video in which I'm going to discuss how to use the determinant of a matrix in order to find the area of a triangle in the rectangular coordinate plane, given that, I know this is a long sentence, given that you know the coordinates of the three vertices of the triangle. Okay, so here we go. But you notice I already started by saying you need to know the coordinates of the three vertices of the triangle. So let's go ahead and what we'll do is we'll generalize this. How about we change the size of this here? Sorry. We'll generalize this as saying, we know the coordinates of the three vertices, but we'll generalize it by saying the first vertex would be x1, y1. We'll call the second vertex x2, y2, and the third vertex x3, y3. But that is, we know the three vertices of this rectangle. What we can do now is we can actually generalize an area formula for this, but we're going to call this A, okay? And I know that I'm using a capital A, and I do in all these matrix videos, but I have to tell you that I'm using A in this instance to denote area. So I guess I might as well just write area. But the area of a triangle in which we know it's three vertices in the rectangular coordinate plane is given by plus or minus, and you might go ahead and start thinking about why I wrote plus or minus, but plus or minus 1/2 times the determinant of this matrix, in which, get this, the first three rows, we'll start them by writing x1, y1, or in other words, the coordinates of the first vertex, or whichever one you want to consider that, x2, y2, the coordinates of the next vertex, and x3, y3, the coordinates of the third vertex. And we're going to fill in this last column over here, this is my favorite part, with just ones. But we define the area of a triangle, given its three vertices, as plus or minus 1/2 times this number, the determinant of this matrix here. Okay, and which actually probably already, you should be begging the question, hopefully, what would happen necessarily if the determinant of this matrix was 0? Of course, you could have three vertices in the rectangular coordinate plane, but if the determinant of this matrix was 0, plus or minus 1/2, or plus or minus anything, I don't care, times 0 is 0. But that would necessarily imply you would have a triangle whose area is 0, which of course would mean that it takes up nothing in 2 dimensions. And so I'll actually challenge you to think about this. In my next video we're going to talk about that, but challenge you to think about what would happen necessarily, or what would necessarily be the nature of these 3 points with relation to one another if the area of that triangle was 0. How would they be related to one another, or oriented around each other? But you might also be asking this question: why plus or minus when we discuss area? Okay, which is a very good question, but you got to be considering the fact that we may be given vertices of a triangle, and they may lie with negative values, or the second, third, or fourth quadrants, in which x and or y necessarily would be negative. But this has the ability to produce a determinant with a negative value, and so in this instance we'd say, since area, we'll consider this two-dimensional measurement. Pardon me. It's always positive. We just use this plus or minus to basically say, look, we're going to end up with a positive area. Okay. So here's what we'll do. We'll go ahead and start with a trivial example, something that you're saying, oh my goodness, why are we going through all of this trouble when we could just calculate the area of it using 1/2 base times height, which is interesting. Recall that the area of a triangle is 1/2 base times height, but we'll just kind of go ahead and set ourselves up here with a rectangular coordinate plane, and how about we make up a triangle? We'll call the first vertex, we'll call this 1, 1. Okay, 1, 1, and how about we go over here? We'll say, okay, this is 1, 4, and then we'll drop in a third vertex. How about we call it? Pardon me, I can't believe I just did that. We'll call this 1, 1, 4, and we'll call this 1, 4, 1. Actually, that'll help me fix that 4 right there. It was ugly, anyways, but. Okay, so we have this triangle, and the reason why I'm picking on this one first is because the fact of the matter is it's a right triangle. So we already know the base and the height, but we say its dimensions respectively are 3 and 1, 2, 3, 4. But we say, okay, 4. So of course, you know what, not that it matters very much, but hey, here's your 3, 4, 5 triangle. But we said we wanted to find the area of this. So of course, 1/2 base times height would necessarily dictate, we'd have in this instance 1/2 times a base of 3 and a height of 4, times height, and we end up with 1/2 of 12, which is 6 square units. Okay, so when we use this formula, we should end up with an area of 6 square units, but keep in mind that most of the time I can't say this because there are just as many right triangles as there are non-right triangles, since they are the sets of those are both infinite and they have the same cardinality. Whatever. I will say this though, you're probably most likely in application problems going to be dealing with things that are not right triangles, and I know I'm going to have people out there scoff at that and scorn me for saying that because we use a lot of right triangles in applications. But anyways, for the sake of these problems, we're going to be using non-right triangles. But let's go ahead and calculate this one here, keeping in mind that we're going to have 6 square units worth of area on this. Okay, so using this formula, recall that we say the area of this triangle is plus or minus 1/2 times the determinant, which we drop in the 3 vertices, which were respectively 1, 4 here. So 1, 4, 1, 1, and we'll go down the bottom right of this triangle. We say 4, 1 here. Okay. Oh wow, I'm just making mistakes left and right. Actually, this was a 5 now, wasn't it? A 5. Apparently, I can count on fingers and toes, but I can't write the numbers when I need to. This was a 5. So excuse me, audience, please. And even worse, here I am ending this matrix, so that wasn't supposed to happen. So this is a quite entertaining video, or not. But anyways, okay, so we filled in the 3 vertices here. I got a little bit distracted by my mistake earlier. We filled in those 3 vertices here, but recall this last column right here just consists of ones. So now we've got 1, 1, and 1, and we need to find the determinant of this. Okay, so now this being a 3 by 3, let's go ahead and use the simple method that applies to all 3 by 3s. We'll extend the first 2 columns. So we're just saying we're taking this first column out here and copying and pasting it here, and extend the second column and copying and pasting it here. But we see the area of this now is given by plus or minus 1/2 times this bracketed quantity. Okay, so here we go. Finding the determinant. The product of the main diagonal here is 1 times 1 times 1 is 1. Plus, no, excuse me, 5 times 1 times 4, which gives us a product of course, 20, plus now 1 times 1 times 1 is just 1. So now there's the product of the 3 main diagonals here. Sorry that I haven't drawn these in. It's just that it's not very easy for me. I happen to stink at using this bamboo, but okay. Minus now the product of the 3 opposing diagonals. So we say 5 times 1 times 1 is 5, plus 1's all the way across the board, which is nice. Nice multiplicative identities. 1 plus 1 times 1 times 4. And here we go. So we say this definition of the determinant here, but let's go ahead and sum these. We have 22, 22 minus 5 plus 1, 6 plus 4 is 10, but 22 minus 10, you notice right there, there's the 12 that we were discussing previously, but 1/2 plus or minus times 12. Now, the neat thing about this is, this plus or minus is nice and everything, but this came out to be positive. Now, if it were negative, we would just, when we take it times plus or minus 1/2, we would apply the negative. The bottom line here is that we just want to make sure that we end up with a positive area, or that you understand that it's positive area. Magnitude is all we care about. So we say 6 units squared are square units. So I think it would be worth our time to run one more quick example in which, maybe not necessarily a right triangle, but let's go ahead and go with this example right here. How about make up some vertices here? How about we go with 1, 0. We'll go with, make sure we get some zeros in there. 1, 0. How about 2, 2. Nice oblique line right there. And then we'll go with, I don't know, like 4, 3. So we've definitely got an acute triangle in this instance, but here she is. Beautiful. And we're going to use our formula. So again, we have 2, 2, 2, 2, 1, 0, 1, 0, and 4, 3. Okay. So finding the area of this, of course, this is not the only way to do it, but this, a nice convenient way to do so. So running our formula, we say the area of this. I won't mess up, I promise. Plus or minus 1/2 times the determinant of this matrix in which we drop in our 3 vertices. So 1, 0, we had 2, 2, and 4, 3. We're just going to go ahead and call these 1s over here. So now let's go ahead and extend our first 2 columns, 1, 2, 4, 0, 2, 3, and we say the area plus or minus 1/2 times this quantity, the determinant of this. So we say 2 plus 0 times anything is 0, plus 1 times 2 times 3 is 6. That quantity minus, now let's go backwards, 0 times anything, 0 plus 1 times 1 times 3 is 3, plus 1 times 2 times 4 is 8. So now we end up with this here, but this is 8 here. We have 8 minus 3 plus 8, of course, is 11, but 8 minus 11, you end up with 3. So this is actually a really good example to show. Actually, I'm happy that we used it. But we say plus or minus 1/2 times negative 3. We're going to go ahead and multiply by the negative 1/2, and observe that it's there, so that we end up with an area of 3/2. Okay, but we say 3/2 units squared. So this is it's a really convenient formula. Enjoy.